Hey, Algebra 2. Today we're going to solve exponential equations. I sort of look at the logarithm section as a method to solve exponential equations because in sciences and engineering there are equations with variables in the exponents that we actually need to solve. And logarithms give us the tools to do that. So it's been 20 many lessons to get to this point, but I feel that we've done really well at building some groundwork to getting here. In lesson 7, a long time ago, we modeled a population of bacteria that doubled every day by the function p of t equals 2 to the t, where t was the time in days. We wanted to know the value of t when there were 10 bacteria. Since we did not know about logarithms at the time, we approximated the value of t numerically, and we found that p of t equals 10 when t is approximately 3.32. Use your knowledge of logarithms to find an exact value for t when p of t equals 10, and then use your calculator to approximate the value to 4 decimal places. Since we have p of t equals 2 to the t, we're doing time at 10. So 2 to the t, find the exact value for time when your bacteria population equals 10. This is where we would take the log of both sides. We're going to do the log base 10 of both sides. And then start solving it. We have to remember our rules for logarithms, that t can go out to the front. And the log of 10 is actually 1. Divide both sides by log base 10 of 2. And we get t equals 1 over log 2. Which, take your calculator and do some math, you get approximately 3.3219, and those are in days. So the population of bacteria is going to be 10 in approximately 3.3219 days. Okay, that was just warming up your brain. Oh, and I gave myself lots of room to do this work for some reason, but I think we got it, so we don't need this slide. All right, let's practice through some exercises. Fiona modeled her data from the bean flipping experiment, which we did buttons in lesson 23 by the function given, and Gregor modeled his data with that function. Without doing any calculating, determine which student, Fiona or Gregor, accumulated 100 beans first, and explain how you know. Let's look at the base. That would tell us, right? Fiona, we are at 1.357, 1.629. Since the base of Gregor's model is higher, Gregor's base is larger. He reached 100 earlier than Fiona did. He reached it first. He reached 100 first because Fiona's base was 1.357. Gregor's model is going to grow faster than Fiona's, and he's going to accumulate 100 buttons before Fiona does. So using Fiona's model, how many trials would be needed to accumulate 100 buttons? If I just use her model, I'm going to plug in 100 equals 1.263, 1.357 to the t. Now, I'm not going to take the log of both sides yet. I want to divide both sides by 1.263. I didn't leave myself enough room, did I? Bummer. I hate when that happens. Those cancel out, and I've got 100 divided by 1.263. You hear me doing some typing here. Sorry, 100. I had something wrong on my calculator. 263, 79.177 equals 1.357 to the t. Log of both sides. Log of 79.177 equals t log 1.357. Divide both sides this way. t equals approximately, and I'm going to take the log of both these numbers, and I still have that 79.17 in my calculator, so as opposed to rounding, I'm going to just enter that in and then divide it by log of 1.357. I get t is approximately 14.3, I don't know how many digits, we'll stick with 3, 20. So time 14.320. So it's going to take 15 trials for Fiona to accumulate 100 beans as far as her model goes. How many trials would be needed to accumulate 1,000 beans? Oof. So going again, I've got 1,000 equals 1.263, 1.357 to the t. I'm dividing both sides by 1.263. Same steps as the last one. And I have 791.766 equals 1.357 to the t. Log of both sides equals t times log of 1.357. Divide both sides by log of 1.357 and I get t. So let's go ahead and take log of 791, etc. And that number's still in my calculator, so I'm going to just grab it and copy it in rather than rounding, because rounding really does hurt our accuracy sometimes. I get t equals 21.86. So in about 22 trials. I love exponential stuff. Like, it took us 15 trials to get to 100, but only 7 more trials to get to 1,000. Crazy, right? All right, using Gregor's model, how many trials would be needed for him to accumulate 100 beans? So I've got 100 in his models on my previous slide, but you've got the paper there in front of you. Let's see, 0.972. 1.629 to the t. So I'm going to divide both sides by 0.972. Sorry, I hear my calculator clunking. 972. I have 102.881 equals 1.629 to the t. Now I'm going to take the log of both sides. T times log of 1.629. Divide both sides by log of 1.629. Those cancel out. I'm left with t equals log of 102, etc. divided by log of 1.629. Time is 9.496, so about 10 trials. And 1,000. You know, I'm going to push pause and do this. You guys try it too, okay? All right, working through 1,000 buttons or beans. I get a time of 14.2, which would be 15 trials. Isn't that so cool? Like, it took 15 trials for Fiona to get to 100, and Gregor is at 1,000, which is pretty awesome, right? That's just how exponential functions work. So, was your prediction in part A correct? Yeah, it was. The base of B made things grow faster, so Gregor got there faster, and our prediction was spot on. Yeah, of course, because we are that awesome. All right. Fiona wants to know when her model predicts accumulations of 500, 5,000, and 50,000 beans, but she wants to find a way to figure out without doing the same calculation 3 times. Fiona, I'm with you. Like, that's a lot of work to do that calculation that many times. Phew. So let's figure it out, okay? Let the positive number C represent the number of beans that Fiona wants to have. Then solve the equation for T, and that'll work. So let's do it, okay? So I've got solve this equation for T. So first I'm going to divide both sides by 1.263. And I have 1.357 to the T equals C over 1.263. Following me so far? Now I'm going to take the log of both sides. So T log of 1.357 equals log of C over 1.263. Now remember, when we have division and logs, they're actually subtraction. So T equals, nope, sorry, erase. T times log of 1.357 equals log C minus log 1.263. Now I'm solving this for T, correct? Okay, I have to come up here, I need more space. I can now divide both sides by log of 1.357. So T equals, my numerator is log C minus log 1.263 all over log of 1.357. There we go. Your answer to part A can be written as a function m of the number of beans C, where C is greater than 0. So that just means that m of C equals log of C minus log of 1.263 divided by log of 1.357. So according to this model, we're going to calculate the number of trials it'll take for Fiona to accumulate C beans. So this model allows us to calculate the number of trials, T, it will take for Fiona to accumulate a number of C beans, or in our case, buttons. So when does Fiona's model predict that she will accumulate 500, 5,000, and 50,000? Well, let me write the model down again correctly. M of C equals log C minus log 1.263 all over log 1.357. So here we're calculating M of 500, M of 5,000, and M of 50,000. You're just substituting 500 in for C. I'm going to write it down this first time, but not the next two. So log of 500 minus log of 1.263 divide by log of 1.357. Make sure you use some parentheses or watch your order of operations, because you can get this one wrong just by making a silly mistake. So first I'm doing log 500 minus log 1.263 and hitting enter. Then I'm taking that answer and dividing it by log of, 1.357. And I got 19.6, or 20 trials. Okay, try that for the next two and write your answers down. I'm going to try them too, and we can compare answers. Hold on, I'll be right back. All right, that's what I got. using my graphing calculator, I actually went up and grabbed some equations and just inserted another 0 a few times. So it was pretty easy, sort of fun. All right, let's try the next one. All right, I need to do a little reminder of some log rules for you all. If I take log base 10 of 10, I get 1, right? How about if I take 10 raised to the log base 10 of I don't care what? We learned a rule that when these match, your answer is basically that, right? And it doesn't matter anything. Like I can say 4 raised to the log base 4 of an apple, just to be super silly. When these match, this is your answer. Right? That's all I wanted to sort of remind you. I mean, it's obviously doing this of actual answers would be, or numbers, log base 10 of 42.57 equals 42.57. And we went through the proof of why that is true quite a few lessons ago. I just wanted to refresh your memory as we get into the next slide. All right, Gregor states that the function g that he found to model his bean flipping data can be written in the form of g of t equals all of that stuff. And that right there is what I want to remind you. We just did a little slide on that. And since log of 1.69629 is equal approximately to 0.2119, he is using this function instead, okay, as his new model. Is Gregor correct? Is g of t equal to that stuff, an equivalent form of his original function? Use properties of exponents and logarithms to explain how you know. Well, let's get the, let's start working, okay? So Gregor is actually correct, but let's try to figure out why. So since 10 raised to the log, if I could spell, log base 10 of 1.629 equals 1.629. We just reviewed that. And 10 raised to the log 1.629t equals, just doing some basic exponent rules on this slide. This is all exponent stuff, right? And again, these two match, so okay, here, let's show you what I did. We said this part right here, log 1.629 is equal to 0.2119. So log of 1.629 is equal to 0.2119. Just did a little substitution there, right? Nothing that we haven't done before. All right, let me get my highlighter out. Okay, log, or 10 raised to the log of 1.629 equals 1.629. Check. And next step, 10 raised to the log 1.629t is the same as 10 raised to the log 1.629. Take this in parentheses and put the t out there. Right here, I can replace this with an actual number because of what we set up here. You can get a calculator out and crunch that number very easily, right? Okay, so Gregor's original model looked like this. Nope, sorry. Ah, that's not an eraser. Ah. So now I can replace this right here with this right here. substitute. Okay, so that right there, like Gregor's right. That simplification, substitution is a reasonable model for his data, right? So with part B, we can actually use it. So write that down. We're going to use it in the next slide. Gregor also wants to find a function to help him calculate the number of trials his function G predicts it should take to accumulate 500, 5,000, and 50,000 beans or buttons. Let the positive number C represent the number of beans that Gregor wants to have. Solve the equation for T. No problem. We are good at this now. 0.972, 10 to the 0.2119 T equals C. So we're solving this for T. First, I'm going to divide both sides by 0.972. Left over, I have 10 raised to the 0.2119 T equals C. Cool. Now I'm going to take log of both sides. So I have so we're up here now. 0.2119 T log of 10 equals log of C over 0.972. Log of 10 is 1, so I have 0.2119 T equals log of C minus log of 0.972. Now I can divide both sides by 0.2119 and I am done. Log of C minus log of 0.972 all over 0.2119. Cool. That right there is the equation I need to figure out how many trials it'll take me to get to different spots. Cool? All right, so your answer to part B can be written as a function n of the number of beans C. So n of C equals log of C minus log of 0.972 all over 0.2119. That calculates the number of trials it'll take for Gregor to accumulate C beans. So write that down. We're going to need that in the next slide. All right, so we're going to use that equation to calculate n of 500, n of 5,000, n of 50,000. I'm going to do the first one, and then I'm going to push pause and do each one after that, because this is just arithmetic. Plug everything in, make sure you keep your parentheses separate to do order of operations correctly, and I got 12.8 trials, which really, so I've got 13 trials to get to 500. And now I'm going to push pause and do the next two. Coming back to you. All right, for 5,000 beans, we have 18 trials, and for 50,000 beans, 23 trials. Pretty cool. Alrighty. Now, Helena and Carl each changed the rules for the bean experiment. Helena starts with 4 beans in her cup and added 1 bean for each that landed marked side up for each trial. Carl started with 1 bean in his cup but added 2 beans for each that landed marked side up for the trial. Helena modeled her data by the function h of t. Explain why her values of A equals 4.127 and B equals 1.468 are reasonable. So Helena started with 4 beans, so we should expect A to be pretty close to 4. And our models are always h of t equals A times B to the t. So a value of 4.127 is, it's close, you know, that's all right. That's reasonable. Because she's using the same rule for adding beans to the cup as we did in lesson 23, we would expect that a B would be about 1.5 if you go back to the work we did in the last lesson. Like, that makes sense. That's pretty reasonable, because this is what we would expect, and that's pretty close to what we got. So I'm good with that. Carl modeled his data by the function k of t equals what you see there. Explain why his values of A and B are reasonable. So what did Carl start with? How many beans in the cup? Just one. So I would expect an A of 1, and we got 0.897. Well, that's pretty close. That's sort of reasonable. And then Carl added 2 beans to the cup for each that landed marked side up. So we would expect the number of beans to double. So we would expect B to be pretty close to 2, and he got pretty close to 2. So they're both pretty reasonable. It's good models, right? Makes sense. At what value of t do Carl and Helena have the same number of beans? So what do we do there? Well, we take the equations and we set them equal to each other. We say, okay, Helena's model and Carl's model, when are they equal? I did not leave enough room for this. So let's see how we can do with our space. I'm going to set those equal to each other. You have these written in front of you, so go ahead and work along with me. So I'm going to try to get t's on one side. So many decimals. I'm going to divide both sides. Well, it really doesn't matter. I can take the log right now, or I could divide the a's off of one side and take the log, but whatever. We're going to take the log of both sides of the equal sign. So I've got log of 4.127 plus, multiplication means addition, so I'm skipping a step here. Log of 4.127 plus t log of 1.468 equals log of 0.897 plus t log of 1.992. Cool? Now I'm going to move the t's to one side and the logs of the constants to the other. We'll keep the logs of the constants on the left for some reason, because that's what I picked. Minus log 0.897 t log of 1.992 minus t log 1.468. Now I have a common denominator on the right, so I'm going to factor out a t and divide what's left over on the other side. So I'm going to skip a step. I'm dividing by everything on the right. All of that is equal to t. If you can see on the right, I factored out this t, and log of 1.992 minus log of 1.468 are left. Cool? Now I can crunch some numbers, get my calculator out, and all of that whittles down to an awesomeness of 5.003. Is that not cool? Now it says use a graphing utility to graph y equals h of t and y equals k of t for that given range. I just used Desmos and copied it in here. And if we drag this down, we're at 5. Awesome, right? Explain the meaning of the intersection point of the two curves. in the context of this problem. The two curves meet at t equals 5. That's where Helena and Carl have the same number of beans. So at the 5th trial, the beans are equal. So the y value is the number of beans they both have after the 5 trials. And if I go back and look, it's greater than 25 and less than 30. So beans would be greater than 25, less than 30, somewhere in there. I can't quite read it. Cool. But we could actually use the equations to figure it out, right? I could plug in t equals 5 into either equation, and that would be how many beans that I had. All right. Which student reaches 20 beans first? Does the reasoning used in deciding whether Gregor or Fiona would get 100 beans first hold true here? Why or why not? Just looking at the graphs, you can see that Helena reaches 20 beans first. But the weird thing is the function that models Helena, what this was, I have to go back and look, the actual function, 4.127, 1.468 to the t. And Carl was 0.897 and 1.992 to the t. We said earlier with Gregor and Fiona that the bigger base will grow faster, But here, if I look at the graph, oops, I'm in red still. If I look at the graphs, which you can go back and peek at, Helena has more beans until your 5th trial, and then Carl has more for the rest of the time. Okay, that's when they sort of flip places. Okay, so after 5 trials, Carl will always be greater, and he's going to reach 100 beans first. The logic that we applied to Gregor and Fiona doesn't apply here because Helena and Carl don't start with the same initial number of beans. Their A term is different. So the same logic doesn't quite work with Helena and Carl, but that's all right. All right, the following functions f and g solve the equation f of x equals g of x. Express your solutions in the terms of logarithms. There's about 6 of these. I'm not going to do them all live for you, but I'm going to do 1 or 2, and you can follow along and look at some tricks and see if you can make your life easier as you work through these. Let's go ahead and start. So first I'm going to set them equal to each other. 10 times 3.7 raised to the x plus 1, 7.4 raised to the x. I'm going to divide both sides by 5. That gives me 2. I don't know why I wrote log. 2 times 3.7 to the x plus 1 equals 7.4 to the x. Now I'm going to take the log of both sides. And remember, when two things are multiplied, that means that we can add them together. When you take the logs, multiplication equals addition, right? I just bracketed that so you could see it a little bit better. I need to distribute that log and through the x plus 1. So here I have log 2. So I'm distributing actually this way. Plus x log 3.7 plus 1 log 3.7 equals x log 7.4. That's a typo right there. It's not really a typo when I write, I know. So that's where we are right now. Let's go ahead and move this to the right side of the equal sign and factor out an x. Do you see the step I just skipped there? I just moved that over and factored out my x. And on the left side, I have log 2 plus log 3.7. Cool? 2 times 3.7 is 7.4. Let's double check that. 2 times 3.7, 7.4. So this is actually log of 7.4 equals x, and I can simplify this to log of 7.4 divided by, I did it again. Did you guys see that? I keep making my 4s 7s. Divide by 3.7. 7.4 divided by 3.7 should be 2. Didn't we just do that? 7.4 divided by 3.7 is 2. So log, oh goodness. Log 7.4 equals x. I'm dividing, this right here is log 2. So I'm going to divide both sides by log 2. And this right here is my answer in logarithmic form, which is how it asked for the answer, right? All right, I'm going to get another slide for this next one. Okay, here's the next one. It's number 6. I'm going to try to work through this without talking through it. So I'm going to show every single step. So please work through it yourself and see if we come up with the same answer at the end. Be right back. Push pause. Okay, I may have shown more steps than you or less steps than you. I tried to show as many steps as possible and color code a few things that may or may not have been confusing. So go ahead and slowly take your time looking through it if we got different answers. On this last thing right here, let me get a red pen, I can actually raise this 15 to the 3rd power if you wanted to, but that's a really big number, so you don't necessarily have to. But I don't know, it was a fun problem. Okay, let's try this next one. Number 7. I'm going to push pause and we'll work through it. So this one actually isn't too bad. It's sort of fun. You end up with with some, trinomials? I don't know, it's a polynomial. So go ahead and try it. That was just like algebra. That was fun. Let's try number 8. I'm pushing pause. I'll see you in a few. That was another fun one. We actually got answers like algebra. Notice here, I did something a little different. I turned them into 4 is 2 to the 2nd power and 8 is 2 to the 3rd power, because then I could take log base 2 of 2, which, remember, when these match, your log is just equal to the exponent. So I did log base 2 of 2, so this becomes my answer. And then this one right here, 2 raised to the 4th power is 16, so that simplified to 4. Sort of fun. Let's see, we have 9 and 10 left to do. So this one's a little different. You're going to need some, well, let's just go ahead and do this one together because you're going to use the natural logs because this one may, I don't know, it's different. So e to the sine squared x equals e to the cosine squared x. Yep. So you take the natural log of both sides. You'll say, oh, well, that was easy. So just like the log logs here, this is natural log, so it's log base e of e. When these match, it gets simplified to the exponent. So here we just have sine squared x equals cosine squared x. I'm going to subtract those from both sides. No, that's not going to work. All right, I was going to use the Pythagorean theorem, but that doesn't work. So here we just have sine x equals cosine x. It would be plus or minus, or it'd be sine x equals negative cosine x. You have two possibilities there. if you think about our identities, we're really stretching back for this one. This would be like a bonus challenge problem. We can say that x equals pi over 4 plus any number, any whole number pi, or x equals 3 pi over 4. You're trying to remember your domain of sine and cosine and where things are valid, and we're really stretching back. And this would be for all integers k, integer being the important word here. All right, let's try this one. May or may not be just as easy, right? So 0.49 raised to the cosine x plus sine x equals 0.7 raised to the 2 sine x. Yikes. So we're going to use a natural log here. So I can say cosine x plus sine x times log of 0.49 equals 2 sine x times log of 0.7. I think there's actually a few things that you can do here. If you can recognize that 0.7 is the same as 0.49, 0.49 squared? No, 0.7 squared is 0.49. 0.7 raised to the second power is 0.49, but I didn't see that first off, so I'm going to ignore that for a minute and see if I can still solve it, just not realizing that little connection. I don't want to distribute that, but let's see. No, I think that's the only way we can do it. All right, going down that road. That would have been another, like, more advanced problem than what I would have expected this early. So I just changed 0.49 to 0.7 squared, which means I can take a 2 out here. Equals 2 sine x times log of 0.7. So that's nice. I sort of have the things on both sides. So I can actually divide both sides by log 7, which is super awesome. Distribute this 2. Then 2 cosine x equals, I can't. I just willy-nilly deleted things when they are supposed to be addition and subtraction. That's awesome. Way to go, math teacher. Can't do that. But I can subtract them, which is sort of fun. So now I have 2 cosine x equals 0, or cosine x equals 0. And when does that happen? Well, we know that cosine of a value is 0 at 90 degrees. For k is an integer. Integer. Cool, that was hard. Last one. Oh, not the last one. This is our summary. Cool. Describe 2 different approaches. I would take the log of both sides and start dividing, right? You could begin by taking the logarithm base 10 of both sides, or the logarithm base 2 of both sides, or the logarithm base 3 of both sides. I would stick with what's easiest in your mind. I always go for base 10. Base 10 makes sense to me. Could the graphs of 2 exponent functions ever intersect at more than one point? Explain how you know. No, you've got a variable not raised to a power, therefore it's going to intersect at one point. And once they cross, they can't cross again, okay? Discuss how the starting value and base affect the graph of an exponential function and how this can help you compare the exponential functions. This is where we talked about Gregor, Fiona, Helena, yeah, and Carl. You can guess how fast something's going to increase by its base, but it isn't always, as long as they start with the same value, as long as the a values are pretty close, the bases are very important and they determine how quickly the function increases or decreases. And then lastly, if f of x equals 2 to the x plus 1, g of x equals 3 to the 2x, is it possible for the equations to have more than one solutions? No. There's only one intersection point. It's raised to an x to the singular value. It's just x. It's not x squared. So it's just going to intersect once. Phew, that was a good lesson. Sort of long though. Sorry.